Hi folks, here's a couple of questions of finding areas under curves. So question number one is to find the area under this curve from x equals 0 to 1. So when we talk about the area under the curve, we talk about the area from the curve itself to the x-axis. Now one thing I notice here is that between 1 and 2, in other words, when x is strictly positive, this function is strictly positive. Okay, so I'm not going to actually draw the function, but just to give you a sense of what we're doing is you have some positive function and we're trying to find the area under that curve. Okay, so that's pretty straightforward because it's just finding the integral of this function from 1 to 2. Okay, so in order to solve the problem, the area is given as the integral from 1 to 2 of the function x times x squared plus 1 to the fourth dx. Okay, so since this function is strictly positive in this region, this integral is equivalent to the area under the curve. Okay, now here this is going to be one of the easier integration techniques, because we see here that we have an x squared plus 1, and when I take the derivative of that expression, I get 2x, which is very similar to the function that I have on the outside. Okay, so let's set that up. We'll let u, our intermediary variable, be x squared plus 1, and now we take the derivative of both sides, so we can rewrite this as du equals, well, derivative of x squared plus 1 is just 2x dx, and so now I notice that in my integral I have an x dx, so I'll just get that on its own, so that's just going to be equal to du over 2. So x dx can be replaced by du over 2, and this x squared plus 1 to the fourth can now be replaced by u to the fourth. So in other words, I'm able to rewrite this integral from an integral in x to an integral in u. So this is just going to be u to the 4 times du over 2. Okay, now this is where we have to make a decision. We either change the indices of integration to u values and then work with this function, or we can just keep the 1 and 2 and at the end replace the u's by the x's. But I think it's quite easy here to just change these into u values, so that's what I'm going to do. So when x is equal to 1, u is equal to 1 squared plus 1 is 2. Okay, and when x is equal to 2, u is equal to 2 squared 4 plus 1 is 5. Okay, so I've completely changed this over from an integral in x to an integral in u. Okay, so now this is a very easy integral to solve. So this 1/2 is just a constant. I can just take that out. And here, of course, the antiderivative of u to the 4 is just u to the 5 over 5. So we have 1/2 times. So here we have u to the 5 over 5, the antiderivative, or an antiderivative of u to the fourth, and we have to evaluate that from 2 to 5, which just ends up being a subtraction. So this is 1/2 times 5 to the 5 over 5 minus 2 to the 5 over 5. Okay, and now I think I don't feel like doing 5 to the 5, so let's just use our calculator here. So 5 exponent 5 divided by 5 minus 2 exponent 5 divided by 5 equal to that, divided by 2. Okay, 309.3. Okay, and so this, as we said, just gives us the area under this curve between 1 and 2. Okay, let's move on to the second question. So this asks us to find the area between two curves. So between the curves secant squared x and the line x minus 1 in this region here. Now again, where we have to be careful is if these functions ever cross, then that will change which function we put first. Okay, but if we take a look at what secant x looks like, okay, pi over 2. Here we've got, and this starts at 1. Well, I know that since I'm only interested from 0 to pi over 4, okay, I notice that secant x is positive there and greater than 1. So when I square it, it's just going to give me something that's again positive. Okay, and we're going up to pi over 4. Now if I look at my other function, x minus 1. Well, pi over 4 is less than 1, so this function is going to look something like this. So x minus 1 is always smaller than secant squared x. So if we're looking for the area between the curves, it's just a matter of subtracting the bigger function by the smaller function. Okay, so in other words, the area that we're looking for, because there's no changes in which one is bigger or smaller, is just going to be given by the integral from 0 to pi over 4, okay, of the bigger function, which is secant squared x, minus the smaller function, which is just x minus 1 dx. Okay. So here, luckily we have that the difference of, the integral of a difference is the difference of the integrals, so we can split this up as the integral from 0 to pi over 4 of secant squared x, and then subtract the integral from 0 to pi over 4 of x minus 1, and each of these individually are easy integrals to take. Okay, so here we remember that the derivative of tan x is secant squared, so the antiderivative of secant squared x is just tan x. So this is just tan x evaluated from 0 to pi over 4. Okay, and then minus, and here we have, well, antiderivative of x is x squared over 2. Antiderivative of x, of 1 is just x, and that's evaluated from 0 to pi over 4. Okay, and fairly straightforward. So here, tan of pi over 4 is our nice one, just is just equal to 1. Okay, minus tan of 0 is just equal to 0, so that's done. Here we have x squared over 2 evaluated pi over 4, so it's pi over 4 squared over 2, minus evaluated at 0, well that's just 0, so nothing there, and then minus again, x, just be pi over 4, minus again 0 is just going to be equal to 0. So here's our answer. Let's just clean it up a bit. So we have 1 minus, so this is going to be pi squared over 16, bring the 16 down into the denominator, so pi squared over 32, and this will just be pi over 4, well, plus pi over 4, because we've got the negative there. And I guess the best you can do here is put everything into one denominator, which I guess will be 32. So here this will become 32. This will remain pi squared, and this is, I guess, going to be plus 8 pi. Okay, and that's as far as you can go. So there's your area. Okay, so just to recap, areas under curves are used by integrating over the area, and you always have to see which function is large. In this case here, this function was strictly positive, so we just had to take a straight integral, didn't have to worry about any negatives anywhere to find areas. And here, because one function was always larger than the other function in the area which we were interested in, it was just a matter of taking the integral of the difference between the larger one and the smaller one. Okay, that's it for these.